So splitting in, quickly go through splitting pattern, splitting in square planar complex. Square planar complex. Splitting pattern in square planar complex. How we will go ahead is, see, square planar complex is simple. That is, you have a, 4 ligands will be there at the 4 corner of the square. How does the octahedral complex look like? You have 4 ligands at the 4 corner of the square, and 2 more ligands we have above and below the plane. Above and below the square we have 2 more ligands. Right? We have 2 more ligands above and below the square. So that means, see, you have a central metal ion above and below. See, don't you think that we will get a square planar complex if I remove 2 ligands above and below the square? Above and below the square, if you place it, that is an octahedral complex. If you don't have ligands above and below the square, you will be having a square planar complex. That means the splitting is easy. That is, we need to know the splitting in the octahedral complex for predicting the splitting in the square planar complex. Splitting in the octahedral complex, as we have seen, you have a degenerate orbital. Degenerate orbitals are splitted into 2 parts. That is, you have a lower dxy, dyz and dzx orbital, dx square minus y square and dz square orbital. Right? This is octahedral field will be splitting. What has been done as far as the square planar complex is, students? For instance, let us imagine this is the z-axis for you. Right? This is our x-axis, this is y-axis. I am just imagining this. So what you have done is, 2 of the ligands which are placed on the z-axis, you have removed it. What you have done is, 2 of the ligands which are placed on the z-axis, you have just removed it. Right? That is what the square planar complex for you. That means 2 of the ligands which are at the z-axis, if you had removed, don't you think that d orbital which has a z component will experience less repulsion? Because along the z-axis you don't have the ligand. Along the z-axis you don't have the ligand. That means that the ligands or that d orbital which has a z component will experience less repulsion. That means again this will be splitted. Are you getting my point? Again this will be T2G orbital will be splitted into 2 parts and EG orbital will be splitted into 2 parts. T2G orbital will be splitted into 2 parts. EG orbital will also be splitted into 2 parts. Correct? That is what happens here is, see, very simple. So in the case of the T2G orbital, what and all orbitals are having Z component? These 2 are having Z component. This doesn't have the Z component. That means it will remain experience more repulsion. But these 2 orbital will be experiencing less repulsion because ligand is not coming along the Z axis. There is a lobe at the Z axis. Although Y axis and the X axis also having the lobe, but there is a lobe at the Z axis which will experience less repulsion because there is no ligand coming along the z-axis for the square planar complex. That means this will be lowered. The triply degenerate orbital will be converted into a doubly degenerate and a singly degenerate orbital, and this doubly degenerate orbital will be converted into again singly degenerate orbital, that is dz square orbital, dx square minus y square orbital. Right? This could be asked, students. It's been asked, that is what is the arrangement of the energy variation. I mean the energy, arrange the following in an increasing order of the energy in the square planar field. Square planar field, what is the arrangement of the energy of the d orbital? That is dyz is equal to dzx, right? Afterwards we have dz square, afterwards we have dxy, afterwards we have dx square minus y square. This is the arrangement in the square planar complex. This is the arrangement in the square planar complex. Are you clear? This is very important, students. We had gone through. Let me just repeat again. You have octahedral complex splitting. T2G comes first, then comes EG. We have tetrahedral complex comes, then we'll be having T2G less than EG, or I can write EG greater than T2G, right? I'm sorry, octahedral complex, energy wise, I'm sorry, very much sorry, EG goes up, right? T2G less than EG, here it is T2G greater than EG, right? In the case of square planar, this is the story. That is dxy is equal to dzx. Dx does square, afterwards comes dxy and dx square minus y square. Very, very significant, students. Just remember, just have to have an idea regarding this. That is, you have removed a ligand which is coming along the z-axis, and hence what has been happened is, since we have removed the ligand coming along the z-axis, those d orbital which has a z component having less repulsion. So law of conservation of energy has to happen. This has less repulsion, its energy comes down, obviously this energy has to go up. This energy comes down, obviously this energy has to go up. This is the splitting pattern in the square planar complex. Now important thing, now coming to the one more very important trick, student. That is, you may be given a ligand, you may be given a complex containing 4 ligands. As I already said, I will give you a small trick for this. 4 ligands. When you are having 4 ligands, it can be tetrahedral, it can be square planar. Clear? It can be square planar. Right? Now the question is, can we directly predict whether it is a square planar or the tetrahedral complex? Can be done, student. I am talking about the square planar in specific. See, square planar complex will be produced by D8 system. D8 system forms square planar complex. One exception we have. That is only one exception, you need to keep it in mind. There is a D9 complex which is square planar. Only one D9 complex which is square planar. Apart from that, all D8 systems are, apart from that, rest of all systems are tetrahedral complex except D8 system. Right? So D8 system, square planar complex, it forms only by the D8 system. In that D8 means 3D8, 4D8, 5D8. In the D8 system, remember, only D8 can form, it may not form. In the D8, we have 3 classes are there, 3D8, 4D8 and 5D8. It's very important, student, keep it in mind. 4D and 5D. 4D and 5D, weak or strong doesn't matter. Weak or strong doesn't matter. It will always and always form square planar complex. Very, very significant point. 4D and 5D, whether it is a weak field or the strong field, doesn't matter. It always forms square planar complex. If at all they are asking you PTCl4, PTCl4 and PTCN4, PTCN4 2 minus and PTCl4 2 minus complex, D8 complex, D8 complex, because it is a 3D system. 3D8, got it right? Because it is a nickel group, it comes, right? Nickel, platinum, palladium we have. That is 3D8, 4D8, 5D8, right? 2 electrons if you are removing, 4s2, 4s2, 4s2. If you are removing 2 electrons, we will be having 3D8, 4D8, 5D8. If at all they are asking you this question, what kind of complex it is, you don't have any problem, because 4D and 5D doesn't matter whether the ligand is weak or strong. This is weak ligand, this is strong ligand, but it is a square planar complex. Both are square planar complex. That is why I said you in the previous discussion that you don't have to have, valence bond theory, you don't have to study. Because valence bond theory speaks about all these things, you need to have an elaborate idea. You don't have to have study the valence bond theory. You can just go through the crystal field theory and you can answer all the questions related to this. So weak field or the strong field doesn't matter. 4D and 5D complexes forms always and always square planar complex. 3D students, only strong ligands will form the square planar complex. Weak ligands will form tetrahedral complex. Very important, this point you just keep it in mind. This is about the square planar. This is about our square planar. Square planar complex will be formed by 3D8 system which are strong ligand, having strong ligand. Weak ligand tetrahedral. 4D and 5D doesn't matter whether it is weak or strong. It will always form your square planar complex. For instance, if at all they had given NiCl4 2 minus and NiCN4 2 minus. What kind of complex is it if they are asking students? Nickel plus 2, 3D8, 3D8. This is a tetrahedral complex and this is a square planar complex. Very clear? Because you have a strong ligand 3D8, weak ligand 3D8. Weak ligand it forms tetrahedral, strong ligand it forms square planar. For instance, if they are giving FeCl4 2 minus, what kind of complex it is? It is a tetrahedral complex because it doesn't matter. All other systems, it is a D6 system, all other systems, whatever may be the nature of the ligand, it will always form tetrahedral complex. FeCN4 times 2 minus if at all there. Strong ligand, don't worry about that. If it is not D8, if it is D8, then only you have to worry about whether it is a strong field, whether it is a square planar or the tetrahedral. If it is not D8, you don't worry, it will always form tetrahedral complex. That is as easy as that. It's a this is a very important shortcut for you for the competitive examination, which will be very useful. Many of the questions can be answered just by knowing the geometry. If you know the geometry, I will give you some other clue regarding the magnetic property and regarding the the magnetic property, color and all. You can easily predict if you know whether it is a square planar or the tetrahedral. See, most of the cases the square planar complexes are diamagnetic and tetrahedral complexes are paramagnetic. This is also a very significant clue for you for the competitive examination. You can answer the question very quickly without wasting the time. Okay, so we'll take a look at students. So we have ended the splitting pattern. Crystal field theory, in a way we have done it, the basic aspect, that is splitting pattern in the octahedral complex, tetrahedral complex and the square planar complex, we have done it. Now what we have to do is we have to take the application part of the crystal field theory, that is we need to predict magnetic property, color, outer orbital, inner orbital complex, stability, all those things at once we will predict it. So since we have done this basic aspect, the foundation aspect of the crystal field theory, we won't be having any difficulty in predicting the property of application part of the coordination complexes under the crystal field theory.